Okay, moving on into 1.3. This is on real numbers in the number line. Every number you know so far is a real number. First, we're going to talk about square roots. A number A is the square root of a number B if A times A equals B. Or if A squared equals B. So the square root is the opposite of squaring a number, and you do need to know the difference between the two. It says give an example of a square root. So the square root of, let's say, 49, because 7 times 7 is 49, the square root of 49 is 7. So to simplify the square root of expression, what you're going to ask yourself is, what number can I multiply by itself 2 times to get that number? So for A, the square root of 81, what number can you multiply by itself 2 times to get 81? And that's going to be 9 times 9, so the square root of 81 is 9. If you have a fraction, you just break that fraction up, and it's going to be the square root of 9 over the square root of 16. The square root of 9, 3 times 3 is 9, so the square root of 9 is 3, and the square root of 16 is 4, so my answer for that one's going to be 3 over 4. There are different parts to the radical. You've got the radical itself, which is that. Then you have the radicand, which is the number underneath the radical symbol. Alright, so guided practice number 1, this is where I encourage you to pause it and try to do these on your own. I'm going to go over them in just a second. Alright, the square root of 64 is 8 because 8 times 8 is 64. The square root of 25 is 5 because 5 times 5 is 25. The square root of 1 over 36 is going to be the square root of 1 over the square root of 36, and that's going to be 1 over 6. Same thing for D. It's going to be the square root of 81 over the square root of 121. The square root of 81 is 9. We've already gone over that. And the square root of 121, while it may not just immediately come to you, 11 times 11 is 121. So the square root of 121 is 11. Alright, a perfect square, you'll hear me say perfect square a lot, and perfect square is the square of an integer. You need to know your perfect squares, and you don't have to memorize them, you can just know how to find them. So an integer is 1, 2, 3, 4, 5, 6, all those numbers. So if you square them, 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. Well, that means 1, 4, and 9 are perfect squares because we squared an integer to find them. 4 times 4 is 16. 5 times 5, 25. 36, 49. You just keep going and you get all the perfect squares. Example 2 says lobster eyes are made of tiny square regions. Under a microscope, the surface of the eye looks like graph paper. A scientist measures the area of one of the squares to be 386 square microns. What is the approximate side length of the square of the nearest square to the nearest micron? Well, if the area of the square is 386 and area equals the side squared, and they're asking me for the side, then all I have to do is take the square root of 386 and I'll get a side. Well, the square root of 386 is not a perfect square, so you'll have to estimate. In the book, if you look at the book, they show you how to do it by doing 19 squared and 20 squared. If you don't have your calculator, if you do have a calculator, you can put it in and you'll get a decimal. Either way, it's going to be closer to the square. It asks you for the nearest micron, so the nearest whole number, and it's going to be closer to 20. So it's going to be, S is approximately 20 microns. Alright, guided practice number 2. What is the value of the square root of 34 to the nearest integer? So what I want you to do is think of your perfect squares. So I already know 1, 4, and 9. 4 times 4 is 16. 5 times 5 is 25. 6 times 6 is 36. So I've got 25 and 36. Well, 34 falls between there. Happens that square root of 34 is closer to the square root of 36, so it means that it's going to be closer to 6 than it will be to 5. So the square root of 34 to the nearest integer is going to be approximately 6. Alright, now let's talk about a set of real numbers. Every number you know so far is a real number. A set is a well-defined collection of objects. You know what can be in it and you know what can't. Excuse my handwriting, it's really hard to write on this iPad. Each object within a set is called an element. And then a subset of a set consists of elements from the given set. You list elements of a set within braces. And you'll see braces a lot. But anyway, this weird looking box here is going to represent the set of real numbers. And I'm going to tell you about all of the subsets of the real numbers. So if you'll just think of this box as the set of real numbers. All of the real numbers in the world fit inside of that box. Then, the set of real numbers can be separated into two sets called the rational and the irrational numbers. Rational and irrational are easy to distinguish because rational numbers can be written as a fraction, while irrational numbers can't be written as a fraction. For instance, any number that is a square root of a number that's not a perfect square. So the square root of 36, that's a perfect square, but the square root of 37 is not. So the square root of 37 is irrational. Also, pi, any decimal that doesn't repeat or end is also irrational. Now, rational numbers are easy. It's the square root of a perfect square. It's a fraction. It's a decimal that repeats. Okay? Then with irrational numbers are their own set. There are no subsets of irrational numbers. Rational numbers have subsets. So rational numbers are any numbers that can be written as a fraction. Well, within that set, you also have the integers, which are the numbers we normally put on a number line. And they're all the negative whole numbers. And then the positive whole numbers. So I normally represent it with -3, -2, -1, 0, 1, and 2. And I just put ellipses on either side to show that it keeps going. Then within the integers, if you take the negative numbers off, you have the whole numbers. 0, 1, 2, 3, and so on. So no negatives. Then within the whole numbers, you have what we call the natural numbers, and I also sometimes call them the counting numbers because it's the numbers you count with. And that's your subsets of the real numbers. Now you're going to have to classify those. So I have 15. What is 15? Well, 15 is it a natural number? Do I count with it? If it's a natural number, it also has to be a whole number. If it's a whole number, it also has to be an integer. And if it's an integer, it also has to be rational. So you have to list all four. B, negative 1.4583. Well, it's not a fraction, but it could be written as a fraction because the decimal does stop. So because it can be written as a fraction, it is rational. But because it's not a whole number, it is none of the others. Square root of 57. 57 is not a perfect square, so that makes that irrational. All right, guided practice. This is where I encourage you to stop and do these on your own. I'll give you a second to pause it, and then I'm going to go through and show you the answers. All right, A, the square root of 9. 9 is a perfect square, so that's actually 3, which makes it a natural number, a whole number, an integer, and a rational number. So I'm going to say natural number, whole number, integer, rational. 3/10 is a fraction, so it makes it rational, but that's all it is. Negative 0.5 is a decimal that can be written as a fraction, so it's rational, but that's all it is. Square root of 12. 12 is not a perfect square, so it is irrational. All right, and blank is a mathematical symbol sentence that compares the values of two expressions using an inequality symbol. And that word I underlined there is your key word. It's inequality. And here's your symbols. Less than, greater than, less than or equal to, greater than or equal to. You do have to know the difference. You cannot write that on your hand during a test. If you do and I see it, you will get a 0 on your test. It's not that hard. You can learn that. All right, so to compare real numbers, the first thing you want to do is put them in the same form. So example 4, they want you to compare the square root of 17 and 4 1/3. Well, the square root of 17 is going to be approximately 4.123. And it does go on forever because it's irrational. 4 1/3 is going to be 4.3 repeating. Well, 4.3 is bigger than 4.123, so square root of 17 is less than 4 1/3. Now I want you to notice how I did change them for my purpose of knowing which one's bigger, but when I wrote my answer down, I wrote it in the form I was given. Again, here I would suggest you pause it and try to do these two. Otherwise, I'll show you the answer in a second. Okay, so the square root of 129 is approximately 11.36. And then you've got 11.52, which is already a decimal. Well, obviously 11.52 is greater than 11.36, so that means the square root of 129 is less than 11.52. Okay, now let's order numbers from least to greatest on a number line. So to do that, you want to put them all in the same form. So decimal form is the best. Square root of 4 is going to be 2. Then 0.4 is already in decimal form. 2/3 is going to be 0.6, so that's negative 0.6 repeating. The square root of 2 is approximately 1.4. And then you've got negative 1.5. When you do things on a number line, I always want you to put 0 in the middle, and I want you to number evenly on both sides. There are exceptions, and I'll show them to you when we get there, but right now you're putting 0 in the middle, and you're putting the numbers evenly on both sides. So if you're going to graph square root of 4, that's 2, but when you label it the square root of 4. 0.4, that's almost halfway between 0 and 1. We didn't have to change it. Negative 2/3 is negative 0.6, which is a little over halfway between negative 1 and 0. and we've got to call it -2/3. The square root of 2 is 1.4, so it's going to be almost halfway between 1 and 2. But when we label it, we have to label it the square root of 2. The next one, -1.5, is going to be halfway between -1 and -2. And now you've labeled and ordered your numbers on a number line. If they asked you to relist them from least to greatest, all you would have to do is look at your numbers from left to right and list them from left to right. Okay, you can pause it here, but I'm going to show you how to do it in just a second. Alright, you want to change them all to decimals. So I'm good here, I'm good here. Square root of 9 is actually 3. The square root of 7 over 2 is 3.5, so that's going to be -3.5. And the square root of 5 is approximately 2.24. So my number line okay, so my first one is 3.5, so that's going to be halfway between 3 and 4. My next one is -2.1, so it's going to be a little bit past -2. My next one is square root of 9, which is 3, so it's going to be right on 3, but when I label it, I need to label it the square root of 9. Always label it what they gave you. The next one is -7/2, which is -3.5, so we'll go left 3 and then another half, but we label it -7/2. And then the last one is the square root of 5, which is 2.24. That's about 2 1/4, so we're going to go right 2 and then about 1/4 of the way to 3, and we're going to label it the square root of 5. Alright, now you've numbered on a number. What I want you to do for your guided questions is on a separate sheet of paper. I want you to answer these 4 questions. You do have to do a number line for number 3 here, just like we just did. If you don't, you won't get credit for it. Make sure if you're in a subset, like if you're in the natural numbers, you have to be in all of the other sets too. Show your work. If there's any work to show, you have to attempt every problem, and that means to do more than just write down the problem. And I'll check it tomorrow.